Good morning, everybody. My name is Talon Myburgh, and I am a second-year master's student at Rhodes University in South Africa. I'm based with the engineers at Fourier, and I have the privilege of being supervised by Professor Justin Jonas. So what started off as a master's degree and just sort of coming to terms with the polyphase filter bank ended up becoming something more detailed in studying the finite precision arithmetic involved in the polyphase filter bank computation. And so to begin, if we look at correlation, if you were to implement correlation outright, you would implement it according to this mathematical equation where you delay the one signal and conjugate it before multiplying it with the other, and then sum for a certain length. And what this gives rise to is what is known as the XF correlator. And so if you were to implement in hardware, sorry about how blurry it is, but you would basically do that. You'd delay the one signal, you'd multiply it with the other, and sum. And then for scientists, you typically require your data in a frequency domain. And so you'd apply a Fourier transform at the end to get a visibility in the frequency domain. The alternative is to follow what is known as the correlation theorem. And if you follow the correlation theorem, you would get a time domain correlation as being the inverse Fourier transform of the Fourier transform conjugated of f of t and g of t multiplied together. If you then just switch the Fourier transform to the other side, you can get a frequency domain based correlation by simply multiplying the two Fourier transforms together. And this is what gives rise to what is known as an FX correlator, which would be implemented as such. You Fourier transform your two signals, you multiply them together and accumulate, and you get your frequency domain based visibilities. So if you were looking at this FX correlator, which is what I'll focus on because it's what's most typically used, if you were looking at where you would find your most quantization error occurrences or propagation of quantization error, it would occur in what is known as the F engine, which is the Fourier transform stage. And the F engine is implemented, as we heard, with a polyphase filter bank. So why we have a polyphase filter bank? I think we've already established it. A DFT alone gives you a lot of spectral leakage and scalloping loss, and you have better control with a polyphase filter bank over your channels. And while it's more computationally expensive, it is worth it. So if you were to implement this in hardware, you would have a sort of design like this. You've got a commutator which distributes your time domain data pointwise to each of your Fourier filters. Your Fourier filters perform a multiply accumulate based on some windowing function that you've specified, and they will then output this result to a point on an FFT, and the FFT will do what FFTs do. And so looking at this, again, if you wanted to sort of outline where would quantization error most affect my result, in the Fourier filters, everything, all the quantization and error is constrained to the point in which it's done. So the multiply accumulate, all of that quantization error does not leak between points. So it all just goes straight into the FFT. The FFT, however, is where we have an issue. So looking at the fast Fourier transform, the one implemented by Casper is a radix 2 decimation in time natural input fast Fourier transform. And this here is just an 8-point illustration thereof. We've got your natural input on the left-hand side in the time domain, so it's all consecutive. And on the far right, you have your bit reversed order frequency domain, which is very easy to reorder. You apply your multiplications with your twiddle factors, which are just roots of unity, really. And this is what is known as a butterfly diagram, and your signal flow propagates all the way through to your result. So now I'd like to take a step back and sort of outline the most essential factors in looking at finite precision arithmetic. And the first up, obviously, is your number system. So you're given a certain number of bits, and you have to represent a real number in these bits. And the sort of limitations on this, or how you choose, well, deciding on your bit widths is often not up to you. You're limited by your storage access permitted, by your precision required, your dynamic range required, what sort of hardware logic do you have available, what is allowed, and then what compute speed is required. And compute speed is going to affect what type of number system you use. And so when I speak about number systems, first up, you've got your fixed point numbers. So with fixed point numbers, it's sort of like your standard decimal number, You store an integer part, and you store a binary part, a fractional part, and you separate it by an imaginary sort of binary point. And so in reality, what you do is you recall the binary point. You memorize, you sort of remember where it is. It's not a real binary point. And if we wanted to do an example, a 16-bit fixed point number with 10 bits allocated to fractional, if we wanted to store that number there, you would scale it up by 2 to the 10. You would store the integer result, and depending on your rounding scheme, which is another thing to address, you would store the integer in binary 252. Returning it, you see you only get 2 decimal points of precision. And so this is an issue with fixed point numbers. You're limited by precision, and I haven't shown it in an example, but you're also limited by dynamic range. And so next up is floating point numbers. Now floating point numbers, they offer a larger dynamic range and precision per number of bits that you use. And they store a normalized real number with a sort of exponential scaling factor. The issue with floating point is that this exponent has a bias applied. And so this bias allows it to be compared lexicographically, but the other issue is it takes away, you can no longer do your standard fixed point arithmetic with it. You can no longer use your same adders to do subtraction, etc. So you need a special unit to do your arithmetic. However, if we put our number in a 16-bit floating point, and you got that binary representation, you would get something returned like that. And you can see that you got now 2 extra decimal places of precision. I don't have an example, but it also increases your dynamic range. So that's far better. Issue is, though, fixed point numbers happen to be rather predictable. You can sort of figure out where you're going to have your issue. Floating point is, it was developed by engineers, so it's just, so those numbers are all fully representable in 64-bit, in fact, even 32-bit floating point numbers. And if you just multiply these two vectors, you dot producted these two vectors together, you get the result 0. In real life, however, you should get the result 2. And this is something that happens with floating point all the time. It's terrible with matrix multiplication, and I know this is not a huge factor in Casper, but it is a factor in data science and those fields. These are not just the only anomalies. You have like multiple representations of infinity and 0 and bizarre rounding schemes and all the rest. And so along came in 2017 a number system called a posit number. And what this does is, in fact, it's a drop-in replacement for 754 floating point numbers. It has a larger dynamic range per bit. It has a higher precision per bit. It has better closure. It's bitwise identical across systems, and I know maybe people aren't aware, but floating point is not always bitwise identical across systems. It has simpler hardware. You can use fixed point arithmetic. So gone as your FPU, you now go straight back to the ALU and you do your integer, your binary arithmetic like that. And exception handling, there's only one NAND value, there's only one 0 as there should be, and there's only one infinity. And what it does is it stores your number as a sort of composite, uses a composite scaling factor to get you the dynamic range, and offers up more space for your fractional. And that's the sort of composite scaling factor. So storing our number again, you get this binary representation. And if you wanted to return it, you get that number. Now I know, again, it's only 4 bits of, 4 decimal places of precision, but if you look, floating point had a 0 there. And that is 8 is far closer to 7 than 0 is. And if we wanted to compute your decimal accuracy using that algorithm, you would see that your fixed point numbers have a decimal accuracy for this number of around 3. So they're around about 3 decimal places of accuracy. Floating point numbers have a decimal accuracy of about 3.9, and a posit number will have a decimal accuracy of 4.5. And the difference between those, between fixed point and floating point and posit and floating point, is nearly the same. So now, this here is just a very blurry graph that I took off a paper, and I was going to make mine myself, but I found it a little difficult. But so here it shows that in and around 0, your posit numbers have a higher decimal accuracy than your floating point. And while it tapers off and floats will dominate on the edges, you also see that it extends, and you've got a larger dynamic range. Not only that, floating points do have an uneven tapering, whereas your posit numbers have a very even tapering on both sides. And every number that is representable, like say 10, if you can fully represent 10, you can fully represent 1 over 10. And what this allows is that multiplication and division are as easy to perform. Same goes for addition and subtraction. The other issue, when once you've settled on a number system, as with Cassper you have, then you've settled on, say, fixed point. And now the idea is, what do you do? How do you treat rounding and overflow? What do you for arithmetic? How do you round with overflow? If you've reached the end of your dynamic range, do you wrap the numbers or do you saturate them? What do you do with exceptions? This is not so much something that happens in DSP, but you got your issues of dividing by 0, you got your logs of negative numbers, and what is of issue is your bit growth handling. How do you handle bit growth throughout? In what I'll address is the fast Fourier transform. So my research last year I presented on a fixed point simulator that I'd built for the polyphase filter bank in Python, and so my research in developing this fixed point simulator required developing fixed point number system, because there's none in Python. And this had to have a NumPy backend to make it a little bit faster. It had to have near full mathematical functionality. I had to be able to represent complex numbers and real numbers. And then off of that, I developed a fixed point FFT, as I showed I showed the algorithm for that. It's an iterative radix 2 implementation. It allows for staging, so you can watch the signal propagation through every stage of the FFT. And it operates in nearly the same way as the Cassper FFT. There are some discrepancies which affect the power levels, but bitwise, it's accurate. What I then did off of that is just to take it a step further and develop a fixed point polyphase filter bank. And this is very generically implemented. You create it as an object, you give it your parameters, and you run it on some data, and it's 3 lines of code, and you have a spectrum. So why build a simulator? I didn't know how polyphase filter banks work, so that's why I did it. I hope it assists with debugging. It certainly has helped me with my study of finite precision in a theoretical case. And I hope possibly it will assist with prototyping. If you're looking to build a new polyphase filter bank implementation and you want a best guesstimate, this is a sort of, if you want to especially take into consideration the quantization effects. So looking back at this diagram, you can see that in this Fourier transform, you have 2 mathematical operations being performed. You have multiplication, where you're multiplying by your twiddle factors, and you have addition, where you're adding your 2 signal paths together. And so multiplication will double your bits and fraction length in fixed point. Addition will only increase your bit length. And of course, when I'm speaking about multiplication here, I'm talking about real numbers, not complex, because then you do perform an addition. But for reals, you only increase the bit length. And so what you do to accommodate this increase when performing addition is you implement something known as a shift register. So the shift register will preempt the addition. It'll preempt the bit growth by 1 at every stage of the FFT. You take in your signal, and what you do beforehand, you right shift at both numbers, and you then apply the addition, and then hopefully it doesn't overflow. It grows back into the space that you've allocated for it. And so I've given a little example here. On the left-hand side, you have full aggressive shifting for a 1K point FFT. On the right-hand side, you have no shifting. And this has a 2-tone signal with a little bit of noise. And if we iterate through it, this is stage by stage through the FFT, what you end up seeing is that on the right-hand side, your 2 tones have leaked into the other channels. And this is a result of not shifting. On the left-hand side, you've squashed your noise a little bit, but at least you have your tones constrained to the channels that they should be. Now, this is something to optimize for. You don't want to overshift because you lose your noise and your sciences in the noise. You don't want to undershift because then you get something that looks like that. And once you get something like that looks like that, it's sort of game over. The other thing to address, you've got your rounding issues, and this is only for a few integrations, so you're not seeing the drastic effects. But with your rounding, far right is floating point implementation, which I also built, a floating point polyphase filter bank. And then on your left, truncation center is your even rounding, and the bottom is just a zooming in of the top. And you have an infinite rounding scheme, in the third place. And as you can see, the noise floor all looks quite different. Infinite rounding, you're rounding away from 0 all the time. And so what it happens to do is it raises the noise floor upwards, especially when taking power, right? It's like taking an absolute value. You raise all the values up. You can also see that the sort of dispersion is a lot larger. Whereas in the even rounding, when you're dealing with very small numbers as your noise floor is, you're rounding to 0. And so you squash out your noise. Truncation performs a sort of weird thing. It almost induces a sort of pink noise into the noise floor. But hopefully no one does truncation. Floating point, well, on 64-bit precision, it does what floating point should be. So in conclusion, I think what is very important to it, what I've found in my study, is that you want to consider the effects of your number systems. So using my simulator that I developed, I'm soon to have a posit number implementation. And what you want to do is you really want to consider what number systems you're using. You want to see if you can optimize it for the hardware. You're often limited. You want to optimize to the shift register. You want to make sure that your tones don't overflow, but you want to make sure you don't squash out all your noise. And that's something to make very sure of. And I think techniques for perhaps optimizing the shift register are essential. You want to accommodate the fact that you've paid a huge amount of money for a very precise or large bit width ADC, and you want to make sure that when you take this into your spectrometer and later into your X stage, you want to make sure that you can accommodate, your high dynamic range of precision. There's no need to do this if you're throwing away most of your information in the Fourier transform. And finally, just something that I thought, in doing this in a completely separate engine, I developed something that could almost be like a sort of like a manual on how the FFT works. It's not necessarily the only way to simulate, but it is a different way to simulate. It's a completely different mathematical engine, and it's sort of it's a very theoretical case, but what it allows for is very fast, rapid prototyping, fast debugging of issues that you can come to expect before you even implement it in Simulink, and perhaps doing this for other DSP, just on a small scale because it's semi-easy, is necessary. Questions?
So you pointed out that the shifting in the FFT is very important, and this is more of a comment and a suggestion, is that we used to do something called conditional shifting, where at every stage of the log-in stages, you would figure out if you need to shift, and you would only shift if you needed to. And then at the end, it would report how many times it had to do that, a block floating point. And I would like, I'm going to suggest, if you don't mind, adding that as a possible thing that you could simulate, because I'd like to encourage us to put that back into our FFT, because it really does improve the dynamic range. It adapts to strong RFI and weak signals. You get the most dynamic range you can.
Yeah, I had just thought to do a similar thing, addressing the power level before, and just running it through the FFT once and populating a shift register, and then reusing that shift register for the full observation afterwards. Almost like calibrating your shift register prior to observation kind of thing. Yeah, something like that.
One more question?
Jack?
So, normal Kasparov, 4 kilopoint, the 18-bit data probably doesn't have any spare RAM to blow it to 32-bit floating point. What should they do? 18-bit fixed point, some custom floating point?
They should use posit numbers. No, there actually are FPGA implementations of posit numbers. The only issue I've come across is that there's only one rounding scheme. You only have an even rounding scheme. So what this does is if you have a slightly non-DC level, a non-zero DC, then what will happen is that you introduce a small bias, which is what even rounding does, as opposed to infinite rounding. But otherwise, optimize your fixed point because it's incredibly fast and supported, and then optimize it so that you're not throwing away, optimize the shift register and all the rest. I think you have a floating point. There is a floating point implementation, but 4K is a bit big, I think, or is it not? Is 4K a bit big for floating point? Does it fit on?
There's a
Yeah.
lot of resources on the PTA,
Yeah.
so I don't think anyone's doing floating point.
Yeah, so stick to fixed point for now, and I'll
Yeah.
work on posit numbers.
But I think we heard yesterday that floating point is going to come naturally in the new DSP block, so that'll maybe encourage us with people that need more dynamic range will be able to do it.
Yeah.
Except it does come with other, as we've seen,
Yeah.
implications. So, and people often ignore that, and then you get weird results in your noise floor that you don't understand.
One follow-up.
No, we're running past now. I'm going to talk to Talon afterwards, but thanks very much.